is that I want to see students from elementary, middle, and high school, and even undergraduate, using the technology that exists right now, cutting edge, in order to model and build the world around them. Okay, let's actually start let's start with something very, very basic. Say, okay, for example, right over here. Okay, I have my iPad on the left. I have my Acer Google Chrome tablet here on the right. But for example, I just want to show you something. Show you this here. Okay, on my desk here, if I may. Let me get the camera here so you can see it. All right. Now, I always love showing the fractal here, but see right here on my desk, I have this rectangular prism, right? And I have a cylinder right next to it. Okay, now I'm thinking 7th or 8th grade geometry here. Okay, see, most math teachers get this impression that, oh, three-dimensional 3D graphing is only for, like, those gifted students, or maybe it's only for students taking like calculus 3, where we talk about directional derivatives, equations of tangent planes and such. But really, 3D graphing is for everybody within elementary, middle, and high school. Because think about it, we live in a 3D world. So why are our students not doing more with 3D plotting? They should be. And many high school teachers tell me, oh, because it's not in the curriculum. Then I say, well, you know what? Curriculum's got to change. You know what? Curriculum has been a fluid document anyway. But see, I have a rectangular prism here. I have a cylinder here. And so I have the kids. And so so I'm actually going to kind of line these up here so that the cylinder is like tangent to the ruler, if that makes sense, right? And I have the prism right here. So if I'm teaching geometry, say, even in like a geometry class or an algebra 1 class, even talk about point plotting. So you know what? I want you to build this in the 3D graphing calculator. And kids are like, huh, what? And we can. Now, I'm not a millennial by any means. I was born in '79, but you know something? Just because doesn't mean I can't create. I like to go to my computer to create, as I'm doing right here. And I literally will go to the 3D graphing calculator. I create in the apps, in the software, and then I actually open up on my iPad or on my phone. Now, this generation likes to create on their phone. But you know what? It doesn't matter. They can create whatever. Okay? So this is where I start creating. And so that prism right there, let me just see it for the most part, but we can start plotting points like this, right? 0, 0, 0, right? And then I think I measured that side was like, it was 8 and 8/10 centimeters, right? So I put a point there. That was that box right there. And so students, even in middle school, elementary, students should be able to tell me what the other two vertices of that base is, right? That makes sense? So see, we're giving them real life experience here, but we're also practicing a basic skill of plotting points in 3 space, if that makes sense, right? Isn't that going to be 8 and 8/10, 8 and 8/10? Right? That's not square. It was actually rectangular, right there. And then what would the coordinates of the 4th point be? 0, right? 0, 8, and then 0 right there. And so now I could use the polygon tool or just do polygon A, B, C, D, right? And there's my base. Now the height of that box on my desk was actually 3 and 6/10 inches. So I could actually just say, okay, prism. I like to use the tools too, but I'm just trying to save time here. But if I go down here and just type in prism, say the base of that prism is going to be Q1, and its height is 3 and 6/10 centimeters. See right there? I literally just made that in a matter of a minute or two. And I want my kids, I want students to be able to do the same thing. Measure objects in the classroom and build them in the 3D calculator. Again, you don't need to know calculus 3 in order to work in here. If you see what I'm saying? So right here, okay, so let's actually quickly show the auxiliary objects so I can hide all those ugly labels. Give me a second. Right, we just want to hide, and I'll sort it by object type. All right, so we can actually hide all those edges there. Give me 1 minute. Just click on the word segment, just right click, settings, and then undo the labels there. There's more there, right? But see, now I have this that I've just plotted right here. And so what do I do? What do I want this generation to be doing in mathematics education, starting now and going forward? Well, let's actually save this, and we can open it up right in our phones. Okay, so I'm going to save this, file save. Whoops, not export. Hang on, I'll download it anyway. Fine. So let me go to File, Save. I'll save it as test box. Right now it's shared with link, but I'll make it a public resource for now, so iOS people can get it too. So it's saving, and then save successfully. Okay, so I go here to my GeoGebra profile, and if you want to open up your phones, let's see if you can all get this here. You are thousands of miles away from me, but I just created this, and we go here. Okay, and there's the test box right there. Oh, it's huge. But open it up. Okay, and try going into, now the easiest way to get it is to just copy the digits of the URL there. So I'm going to actually paste it here. If you go into open up now, watch this. If you open up your 3D graphing calculator on your phone, okay, or I'll do it on my Chromebook tablet here. All right, so go here now. All right, and let's go to the 3D grapher. And where it says up there, go to open. I think in the iOS it says search. I think those words aren't exactly the same, but that's okay. So the easiest way is to type in that URL right there. That should make that resource show up instantly. Okay, and I'll make this bigger so you can all see it. All right, even bigger. So let's type in WY. It is case sensitive. RFW FNQ. And enter. See how test box, now I could have typed the word test box, but there's some other ones out there with that title. So I click on it. All right. And then look at that. It's right there. And now the students in our classroom today, what can they do? They can actually take their phones, their iPhones, their Androids. I'm going to hit the AR button now, and I'm going to actually test this and see if it works. You see, this is the beauty that augmented reality, ladies and gentlemen, brings to the table that has never been able to brought to math ed before. We want students to model. There's no math teacher in the world that'll tell me that modeling is not important, because we all know it is, right? But let's go one step further. After students build the models, here it's like, well, how can I test it? Unless I have a 3D printer, I'll get Diego to come and just print this out for me and see if I can see how well it fits. But another means, and I'm not knocking that, we should be doing that. But here, you know what? Let me hit the AR button in the corner there, and I'll actually aim it at the floor. All right. If you have an iPhone or an Android, you'll see a little square. But on the Google ones, on the non-iOS ones, you see like a isometric graph paper kind of thing. So touch the square. There's my box. Now the key is to move slow. Just see how it kind of froze on there. I'm moving too fast here. Let me. If that happens to you, just hit 3D. Whoops. Hang on a second. Great. All right. Let me close that out. Sorry about that. Yeah. Close that. That normally does not happen. Sorry. I'll try typing in test box. Oh, there it is. Oh wow. See, it appeared back up. It's magic, right? So I'll hit AR again. I'm gonna go really slow this time here. Aim it on my desk. View, that's better. I got it right there. And then now this is the icing on the cake, ladies and gentlemen, right here. The key is to superimpose it perfectly over what you have there. Now I get we're not shooting a rocket to the moon here, and maybe I got the link with wrong, but the thing is, no matter how you slice or dice it, it should fit pretty well. All right. Now, if you actually make these, it's a little shaky, but if you make these coordinates in terms of sliders, you can actually, slide there. I think maybe I messed up one of those dimensions there, but that's the whole point there. Now, if you go to open again, I'll show you this. It is in here. I'm actually going to do it on my iPad. All right. Right here. Okay, open up 3D graphing calculator right there. Go to search, and I'll just type in, if you type in the word STEAM, it should pop up, STEAM. I have 3 demos here. If you go to demo 3, that's what it was right there. not that you have these objects in front of you, but I went to the Steam and it said demo 3. I built this early this morning here just to test it out, and I'll show you the quick demo here, at least on the iPad. All right, here we go. Putting in augmented reality. This is what we need to have our students doing more of. This, I mean, come on, you can go to like an IKEA or something like that and use their augmented reality app. There we go, that's a lot better, right? You can use your augmented reality app, right, to see how something fits in your living room, all right? But here, you know what, augmented reality, let's use that to students' advantage. They not only have to build it, but they need to be able to, they should be able to virtually test the models as well. I think the tangency kind of got messed up here. Let me, hang on a second. Make sure, I'm just gonna line these up quickly again, because I think they came a little off. That's better. Just lined it up with the ruler. And now, let's test it again. The cool part is with these things is that if it's built pretty well, it wants to glue itself to the objects, like right here. Now it's kind of glued well, but I'm backing up. But no, it did it this morning. But see here, it's actually kind of right there. All right. So again, we don't need to be in a super high level calculus class in order to in order to be able to build these things. We could do it in elementary and middle school, and we should be starting there. Okay. Let's talk about something else in terms of modeling. Then we'll go to the higher grades and the higher courses. All right. Let's talk. And this, Jules is going to chuckle here, but isn't this every math teacher's favorite candy right here? I use this example a lot from Switzerland, right? Why do math teachers love Toblerone so much? Anybody? Can't see you because you're down there. Let me see. Why do we love Toblerone so much? What can you tell me about it? Say it again. Yeah, it's the only thing in life that I can think of that comes in a triangular prism, right? I mean, rectangular prisms, we have tissue boxes, we have whatever, and but for triangular prisms, there's not a whole lot of things. But here, Toblerone is a triangular prism. But even better, talk to me about the base of that triangular prism. What kind of a triangle is that? Very good. And so now, let's actually visit geometry class in 8th and ninth grade, and let's have them build this model here. They can do it. And I work with you as teachers and students. I'm telling you, our kids can do it. Any students who've studied equilateral and isosceles triangles, especially in the context of coordinate geometry, should be able to build this in the coordinate plane. Now, I do have data here. This thing is 21 centimeters long, and it's 3.5 centimeters. This edge right here is 3.5 centimeters. That's 21 centimeters right here. Okay, so let's actually take now. To say now how we would actually build this in. I'm not actually going to build the whole thing right now, but you're going to help me walk the kid through it because I have it built already. I'm going to show you in a second. But if you're the teacher in a geometry classroom, say, right? Let's go here. Let me go back and just go to new. Oops, minimize that. Let's go here to the 3D calculator. And so again, I have an equilateral triangle right here. Okay, I'll just show you kind of holding it right there. All right. So here's what I'm thinking. All right. We could probably put a point at, say, maybe now this actually was 3.5 long. So not to guide students thinking too much, but you see what I'm saying? I might want to put a point here. Oh, you see how that's half of 3.5? And so the other coordinate would be what? -1 3/4, right? That's half of 3.5, right? So I'm actually building this literally to scale here in the 3D app. Now I could do this on my device as well, but again, I'm choosing not to here. But let me actually, I'm gonna actually give me 1 second. I'm gonna move this over so it's easier to see. Okay. Now, can anybody in the room here help me out? I'm gonna put the third vertex somewhere on the positive z-axis. But the question is, see right there, that's like -1 point. Right here is -1 3/4, 0, 0. Right here, that's point B right there. This is point A right here. I need to put a point C up here. Can anybody tell me what the coordinates of that point C has to be? You got to shout it because I have earphones, but I still need to hear you. The guy across the street's mowing his lawn. Go figure. Well, it's definitely 0, 0 something, right? Well, what's the third coordinate? See, this is what our geometry kids need to be doing. Because if I think about it, if I slice this in half, what kind of a triangle do I get on each side? Yep, we do Pythagoras' theorem, right? Which is what I would encourage the kids to do. But isn't it really basically that shorter leg times the square root of 3? Yeah, and so exactly, and so right here, if I make the polygon here, all right, your kids can build this. All right, where's the polygon tool? I always get blind when I'm doing the presentation. Polygon, there it is. Whoop, right there. So let's make that polygon now. And now, wait a minute. Isn't transformational geometry a vital part of any geometry curriculum, right? So don't we need, instead of putting more points on there, can't we just translate that triangle so many units down the y-axis, right? So let's make a vector. Let's make a vector say that's the length of, isn't the y component the length of the prism, which is actually, it was actually 21, 0. And that vector is called u, and so now I can simply translate. I can translate that T1 triangle by vector u, and ladies and gentlemen, there you have the basis of your Toblerone right there. Okay, but I actually already did the work last night for this, and so if you want to open it up, feel free. And if any of you have a Toblerone on you by chance, I don't know what the chances are of that, but if you go to the store tonight, get a Toblerone and open up this file, see how well it fits. You're more than welcome to try. But if you go open up the 3D graphing calculator on your device, okay, I'll show you exactly where it is. You can find it. It's right here. Whoops. So if we go to search right here, and just type in the word STEAM again, it's actually demo 1 right here. Innovation STEAM Conference. If you just type in the word STEAM to search, is that appearing for you by chance? Are you finding that in your menu when you type in the word STEAM? Okay, so hit demo 1. All right. Basically, you could zoom in and out. That's literally what I built last night, and that actually is the Toblerone. I'll actually demo it here for you really quickly. But yeah. So now I hit the AR button. Wait for the magic square. Hang on. Needs that nice light source there, but because I have a black desk background here, I'm going to put on white paper the Toblerone here. Okay, and let's take this guy and let's superimpose it and see how well it fits. Check it out. Now your kids, we could have our kids making screencasts. And look at that. It actually latched itself right on. And watch this. This is the magic of augmented reality. The better you build your model, you back away slowly, it actually stays glued to the model itself. I am backing away at a very slow rate, but check it out. That virtual model, it's off a little bit, that virtual model we built in GeoGebra, I'm like, look at that. That's crazy. Isn't that awesome? It's my favorite app of all time. It's just unbelievable. Okay. Now, here's another challenge I have for students. There's your first task. Here's your second task. I want you to take 2 Toblerones now, and see again. Joel's asked me to talk about math in the future. This is what I'm envisioning, which is what I want to have happening today. Kids can do this in geometry, algebra 1, algebra 2. We should be having them do it right over here. Now, I actually, all I did is I actually found the midpoint of that edge there, and I have 2 Toblerones now. This base is meeting the midpoint right there. And so now if we go back, hit 3D, go back to search one more time. And let's go to Steam. Type in Steam for search and just type in demo 2, that right there. And that's actually that model built right there. So if you are daring and want to buy 2 Toblerones later after the conference, feel free, and you could play with this. And by the way, you can mess with everything here. I actually made it a sliding scale pretty much, that it's like proportion. You see what I'm saying? If you look at the coordinates, it'll make sense. But let's see how well the model fits. Again, your students will always need time to make these. It is imperative that we give our students time to build instead of just direct lecturing, which I know you would all agree with. But the thing is, if we live in a 3D world, tell me why teachers are only sticking to the coordinate plane. That makes no sense to me. We should be modeling in 3D from early on. Okay, look at that. The kids can do that. Now, think of all the concepts that they have to integrate together. They have to talk about algebra, like coordinate plane. We're in the coordinate plane, but also in 3 space. We have to talk about geometry principles. Oh, properties of equilateral triangles. We're integrating it into one beautiful app here called GeoGebra 3D with AR. And yet if students are able to do something like this, make a screencast and they send it to their teacher, then any kind of paper test, which is really lower level thinking questions anyway, is going to be kind of like, for most, like a joke, if you will. All right. So that's an idea. Let me just present to you one more idea before I talk about, like, math is really an art, using AR for art, if you will. Right over here, if I may. Let me see here. Get my camera back. Here I have a cone. Okay. Actually, before I show you that, let's go to the AR app one more time. The 3D app. I'm sorry. Would you please type in the word surface and then template, TEMPLATE. There it is, yes. If you type in surface template, it's either one of these. It looks like a cone. See how this one here says surface of revolution or surface of rev? It says augmented reality template. Would you click on either one of those, please? Like this one right here that I'm pressing right there, or the second one from the top. Okay. We could build this, but I don't have the time to do that right now. But I want you to note 3 things here. All you have are 3 items. You have a piecewise function. You have a function with restricted domain. Don't most kids know what y equals x looks like? They should, right? You have a slider called angle, and you have this other command called surface. Now, Algebra 1 students are not going to know what the heck this means. They don't need to. Neither do calculus students. But point is, let's slide that slider here. Now, this is a resource that geometry teachers in middle school, right, and calculus teachers in college could use this same resource, but for 2 different reasons. For geometry in the younger grades, don't kids struggle to describe the 3D solid of revolution that's formed by rotating an object about a line? Here, they can jump out of their seat and tell you it's a cone, right? But the AP Calculus students, why do they need this? Because they want to see what the heck that solid they're finding the volume of in Calc 1 or Calc 2 actually looks like, if that makes sense. So now, let's project this in augmented reality. All right, keep it right there. There it is. Hit. Aha, look at that. So now, if you're an Algebra 1 teacher, your kids can now do this. I have a cone that I quickly made before. The radius of this cone is 2.5 centimeters, right? The height of this cone is 10 centimeters. Now, I asked my students, let me actually change the color here to get it to be seen better. In 1 second. That's much nicer. I love that blue. It's my favorite color. Now, I want you guys to role play the student. Is that a good model to model this cone that I have right here? What do you think? No. So you got to shout because I'm having a hard time hearing you. What do I need to do to my function here in order to build this model? Kids are now creating. You see, this is higher level thinking. This is not solve for X. So yes, we need a little bit of that procedural algorithmic stuff. They need to know the concepts, but we need to have our kids create. That's so vital. Tell me how I have to change. What has to change here? Anybody? So 4 has to change to what? Not 4, but again, what part of the cone is going along the x-axis here? The radius or the height? The height here is 10. Now I have to actually go back out of at 3. I have to actually zoom out a little bit to actually get this whole thing, right? But now let's go back here. There we go. So I'm going from 0 to 10, but tell me what about that linear function has to change? We're going from 0 to 10 now, but what else has to change? It's what? Anybody? I'm not sure, but if someone said slope, that's right. But wouldn't the slope of this be 2.5? That's the rise. Isn't the radius the rise and the height's the run, right? 2.5 to 10. See right there? See how look at that equation now. It's y equals 2.5 to 10 x. There it is, and look at this. Your kids build this. There you go. And look, if I move it, see how it wants to move along with it? The better you build your model, it literally wants to be it's like magnet to the thing itself. It's pretty cool. But we're just beginning to scratch the surface here of what we can literally do with augmented reality. One last little thing. Talk about math as an art. How about students learning trigonometry? Let's actually go to 4. You could change this. Let's make it the sine function. Ooh, what does that look like? What do we have here? A fish, right? Now, put it in AR one more time. Yes, we can go inside it. But here's what I love to ask Algebra 2 students, and actually whatever, and talk with functions. How can we actually put a mouth on this fish? I want to open a mouth right over here. Again, math is an art. We're actually having kids work with these functions, but to create artistic pieces. And we're just starting very basic right now. Never mind, we can do so much later. I know I'm almost out of time, but what would I need to do in order to put a mouth on this fish? Anybody? I mean, the function's not going to change. Let's keep the tail there. But what about that 0? What should that 0 change into maybe? To open it, maybe point 2. Ooh, yeah, right. And now I have an activity that asks kids to make 2 kissing fish, and they have to recall the sine function is odd. So if I go from -4 to 4, see what I mean? But obviously, part of my AR window's chopped out. If I go back and zoom out and go back in again, I'll be able to. But see how kids in calculus can understand cross sections conceptually. All right, math is an art, and having kids create. One more thing, um, I want to just show you one thing. You know those calculus questions that kids always have a hard time with, where they have a solid with a certain base and a cross section that's parallel to the y-axis is a whatever, right? But let's type in the word heptagonal. Heptagon. Let's try heptagon. Let's see here. That's not an often one. Heptagon. Oh, all right, let me go back here. Search. Let's type in modifiable, modifiable, modifiable solid, and then enter. There should be a couple that show up here. Any one of these that has a blue background. Here's the heptagonal ones right there, I think. Whoops. Yeah, this one was a pain to make, but here, cross sections parallel to the y-axis are regular heptagons. Second, and in essence, uh, custom solid. All right, 30 more seconds, I promise. I know 10 type of questions here. All right, let's just do the rhombus one. All right, I like to ask kids questions about atypical solids. Like right here, for example, You know what? It's cool to see in 3D, but I think augmented reality puts it in a whole different perspective, in my opinion. But right over here, we could change. We have an upper and lower function. I just got to find the slider here. And all of these resources are in those two volumes that I sent you. Uh, in that first link here. Here it is. If I take the filling and reduce it, right? You see how I can clearly see the cross sections here. The cross section is a rhombus with a 60-degree angle. Hold it to the floor. Let's put it in AR. Let's bring this guy right up here. Now we can actually watch what happens here. We could change that. We could change the angle of that rhombus. That's how I made it. Let's see, move me. You could actually see cross sections literally being formed here. And so now when kids actually say, it helps us visualize what the whole concept of a cross section actually is. There's a lot of ready to use resources that are built right in there. You can go inside, you can do whatever, but this is what I'm envisioning in the future, to having kids mostly modeling and creating their own art. And to me, it's such a beautiful winning combination. It's an amazing app that Team GeoGebra has built, and I love it. And I'd love to see more of it in the math classroom. And when I do go back to the classroom full time, I know I will. My kids will be playing with this from like day one. So yeah, thank you. Any questions? I could see him all from Robert's computer. He has it angled. Yeah. Yes. Mm-hmm. Oh, yeah. I think it's in terms of that perspective. I know I focus mostly on pedagogy in the classroom, but I'm thinking, let's suppose you have a piece of furniture that has a broken leg, like that end table that was your great great grandmother's thing that's been passed down through the generations, right? And all of a sudden it breaks. But now you see like it looks like you see like maybe one of those legs looks like an ellipsoid, right? With you could find your A, your B, your C, right? And then now build it in GeoGebra, have a 3D printer there, and you could actually take the time to print it and actually put it right back on there. I've heard of this being done already. It's pretty amazing that you can build 3D replicas mathematically, and then